Hello students, I am back with the topic of dimensional analysis. In the previous lecture, what we have discussed was the types of variables and constants, and thereafter we have discussed the uses of dimensional analysis, right? There are three uses of dimensional analysis. One is it can be used to check the correctness of a given relationship between different physical quantities. What I mean to say is that if a formula or a mathematical relationship between different physical quantities is given, then we can check with the help of dimensional analysis whether the given formula is dimensionally correct or not. And here I must again mention the principle of homogeneity of dimensions. For a given formula to be dimensionally correct, the dimensions of each and every term on either side of the equation must be same, it must be constant, right? So that was the first use. Second use is, which we are going to discuss in this particular lecture, if there is an occurrence of a physical phenomena involving maybe certain physical quantities, then dimensional analysis can be made use of in determining the relationship between those physical quantities involved in that particular phenomena. That's the second use. And third, obviously, it can also be used to convert from one system into another system. So, let's make use of dimensional analysis in finding the formula or finding the relationship between different physical quantities, right? So, use number 2. To find relationship between different physical quantities, between different physical quantities involved in a phenomenon, involved in a phenomenon. Right? That's the second use. Let's take an example. We all are aware the mechanical energy, the types of energy which a body can possess. Mechanical energy, as you are aware, it can be divided into two types, kinetic energy and potential energy. Now suppose a body of mass m is moving with velocity v. So it must possess energy by virtue of its motion. And that energy possessed by a body by virtue of its motion is known as kinetic energy. So what are the physical quantities involved in this case? Energy by virtue of the motion of the body, that is kinetic energy. The amount of matter contained in the body, mass may be involved in this phenomena. Kinetic energy might depend on mass, that we'll check. And then motion, obviously velocity of the body. So what are the physical quantities involved? Kinetic energy, mass, velocity, right? Let's try to find out a relationship connecting these three physical quantities. Let's proceed. Kinetic energy is suppose E. It might depend upon the mass of the body. How it depends, we are not sure. That is what we intend to do. We need to find out the relationship. But how it depends on mass, we are not sure. Suppose it is m to the power 0. It means that energy do not depend on mass. If it is m to the power 1, it means that energy is directly proportional to the mass of the body. If it happens to be E is proportional to m to the power 2, it means that energy is proportional to the square of the mass of the body. But the point here is, we are not sure about it. How the energy depends on the mass in this phenomenon. So what we do is, we write it as A. The value of A is to be determined, right? So put this as equation 1. Second is, the energy possessed by the body will definitely depend on its velocity. Again, how it depends on its velocity, that we are unsure. It may be directly proportional to velocity. It may be directly proportional to the square of the velocity. It may be inversely proportional to the velocity. We are not sure. So what we do is, we write another variable as b over here. So put this as equation 2. So energy may depend on mass, kinetic energy may also depend upon the velocity of the body. How it depends? That is what our intention is. By using dimensional analysis, we need to find that, right? So I hope this first step is crystal clear, right? Now what to do is, from 1 and 2, or combining 1 and 2, what we get is, it can be written as E is proportional to m to the power a, v to the power b, right? Also you are aware, in order to eliminate this proportion sign, you need to introduce some constant of proportionality. It must be a dimensionless constant. Either you can introduce now or you can introduce in the later part, right? Anyway, now what we need to do is substitute the dimensions of each and every physical quantity. Next step would be to substitute the dimensional formula of each and every physical quantity. What is the dimensional formula for energy? It is m1 L2 t to the power minus 2 proportional to. What is the dimensional formula for mass? It is m. What is the dimensional formula for velocity? It is L t to the power minus 1. Clear, students? So what to do is m to the power a, L to the power b, t to the power minus b. And over here it is m to the power 1, L to the power 2, t to the power minus 2. I am very sure up till now there shouldn't be any sort of problem. Now what to do is we need to apply principle of homogeneity of dimensions. Obviously we are determining the correct formula or the correct relationship between these physical quantities. So it needs to be dimensionally consistent. And for an equation to be dimensionally consistent, the dimensions of all the terms on both sides must be same. So the dimensions of left hand side and the dimensions of right hand side must be same. So as per the principle of homogeneity of dimensions, a must be equal to 1. Here it's m to the power 1 and on the right hand side it's m to the power a. Right? So a should be equal to 1. What about b? b should be equal to 2. And over here also you can check minus b equals to minus 2. You will get the same result obviously. So we have obtained the value of a and b, isn't it? Now substitute this value in equation 3. What we get is E is proportional to m to the power 1, b to the power 2. Now as I have stated, in order to eliminate this proportionality sign, we need to introduce some constant. So here, suppose this constant is k, small letter k, mv square. This is the relationship between kinetic energy, mass and velocity of the body under consideration. Here I must mention that k is a dimensionless constant. It is a dimensionless constant. Please do remember this. It is a dimensionless constant, right? And one of the drawbacks of dimensional analysis is that it can't be used to determine the value of k. The value of k can't be determined using dimensional analysis. The value of k has to be determined either experimentally or by some other method. It is found, experimentally it is found, the value of k to be half. Right? So, the formula for the kinetic energy becomes half mv square. This is the derivation of kinetic energy possessed by a body by virtue of its motion using dimensional analysis. Right? It's a very simple method. Let's concentrate on another numerical, right? Suppose, let us consider a body to be rotating in a circular path. We are aware whenever a body rotates along a circular path, then the nature of the force involved is centripetal, right? So whenever a body moves along a circular path, the nature of the force involved is centripetal. So a body of mass m is moving in a circular path of radius r with uniform speed v. Using dimensional analysis, find out the formula for the centripetal force. So students, let's do it. So what I have considered is a body of mass m moving in a circular path of radius r with constant speed v. So we are supposed to find out the formula for the centripetal force involved in this phenomena. So first step is force in this phenomenon. It may depend on the mass of the body. How it depends, we are not sure. Second, the force may depend on the speed with which the body is making the circular path, that is v. Again, how it depends on the speed, we are not sure. Third, the force may also depend on the radius of the circular path, right? So it is r. How it depends, again we are not sure. It might happen that this physical quantity may be independent of other physical quantity as well. In that case, the value of the power would be 0. But here we are unsure. We need to find out those values, right? So these are the values which we are not aware of. So let us represent these unknown values by A, B and C, right? So now combining these three, what we get is f is proportional to m to the power a, b to the power b, r to the power c. Now, as per the principle of homogeneity or dimensions, the dimensions of all the terms on both sides must be same. Therefore, the next step what to do is we need to substitute the dimensional formula of every physical quantity. Right? Let's do it. Force, its dimensional formula is mLT to the power minus 2. Mass, its dimensional formula is m. Velocity, its dimensional formula is Lt to the power minus 1. Right? Radius, its dimensional formula is L. Its dimensional formula is L. Now let's keep on solving it. Right? So, m to the power a, L to the power, over here it's b and over here it's c. When the base is same, then the powers get added up. So L to the power b and L to the power c. It will give us L to the power b plus c. And t to the power minus b. And over here it is m to the power 1, L to the power 1, t to the power minus 2. So what do you get? The dimensions on both sides must be same. So what is the value of a? A is equal to 1. What is b plus c? It is equal to 1. What is minus b? It is minus 2. Therefore b is equal to 2. Knowing the value of a and b and substituting it over here, we can easily get the value of c. Therefore, the value of b is 2. So 2 plus c is equal to 1, or c is equal to 1 minus 2 implies that c goes to minus 1. So we obtained the value of a, we obtained the value of b, as well as we obtained the value of c. Right? This is how the values of the unknown values a, b, c are to be determined. Now we need to substitute this value in this equation. We need to substitute this value. So what do you get? F is proportional to m to the power a. The value of a is 1. B, the value of b is 2. And r to the power c, the value of c is minus 1. So we can write it like this. mv square divided by r. Now as I stated, in order to eliminate this proportionality sign, we need to introduce some constant. So f is equal to k mv square by r. This k, again I am mentioning and I am stressing on this particular fact that k over here is a dimensionless constant. Dimensionless constant. Right? It's having a constant value but no dimensions. Right? It is only then they can be dimensionally correct. So, again, one of the drawbacks of dimensional analysis is that dimensional analysis can't be used to determine the value of k, which is a dimensionless constant. The value of k is to be determined either experimentally or by some other known method. Right? Over here, the value of k is found to be 1. Therefore, the formula for the centripetal force becomes mv square by r. So this is the expression for the centripetal force. I hope students you have understood the concept, right? How to derive the relationship between different physical quantities involved in a physical phenomena, right? So this was the second use. One more thing, third use. We can proceed with several other numericals as well, right? But for the time being, let's discuss the third use of dimensional analysis. Third use as stated. Dimensional analysis can also be used to convert from one system into another system. It can be used to convert from one system into another system. Let us finish all the uses of dimensional analysis and then we can concentrate on some more numericals based on the above topics, right? So third use is, it can be used to convert one system into another system. Conversion of one system into another system. So let's see. Let us consider a physical quantity x, and as you are aware, a physical quantity is represented by its numerical value along with its units, right? Suppose n is its numerical value and u is the size of the unit, right? Now numerical value of the physical quantity can change in different systems when we use different units, like 1 kg, it's 1000 gram, like 1 kg. X is suppose mass, it is 1 kg. It can be written as 1000 gram, right? This is N1, this is the size of the unit U1. This is N2, this is the size of the unit U2, right? So what I mean to say is that if the size of the unit decreases, the numerical value of the physical quantity must increase and vice versa. Clear? So therefore, it can be written as NU. It may be written as N1U1 is equal to N2U2. Right? It's constant. It's constant. Now suppose this physical quantity has the dimensions of A, B and C in the basic units of mass, length and time respectively. Its dimensions, whether we consider one system or the other system or the third system, the dimensions of a physical quantity in all the systems will remain same. It's the numerical value which will change, right? Let us consider this to be system 1, this is system 1 and this is suppose system 2. Here a physical quantity x is given. Its numerical value in this system is N1 and its numerical value in this system is N2, right? It can be any systems. Suppose its unit is M1, N1 and T1. These are the fundamental units of mass, length and time in system 1. And suppose M2, L2 and T2 are the fundamental units of mass, length and time in system 2. And as I stated, if you consider a physical quantity, its dimensions on both the systems must be same. We are talking about the same physical quantity. So its dependency on mass, length and time in both the systems will be same. Therefore, let us consider its dimensions in mass is A, its dimensions in length is B, and its dimensions in time is C. So let us assume this case. Now since N1U1 is equal to N2U2, therefore N1, now U1 may be represented as M1, its dimensions is A, L1, its dimension is B, T1 time, its dimension is C. This is the first system in which the units are M1, L1, T1. These are the basic units. If you consider the second system, here the numerical value of the same physical quantity is N2, while the unit over there is M2, L2, T2, and the dimensions will remain same. So it may be written as M2 to the power A, L2 to the power B, and T2 to the power C. Right? We need to find out if N1 is given, N2 is to be found, then the formula for the N2 would be N1. Simply rearrange the terms. What do we get? M1 by M2 to the power A, L1 by L2 to the power B, and T1 by T2 to the power C. So this is the formula which we can use to convert from one system into another system. Right? This is the formula. N2 is the numerical value of physical quantity x in system 2. N1 is the numerical value of the physical quantity x in system 1. Clear? So using this, one system can be easily converted into another system. I'll give you a simple illustration. Let's make use of this concept in finding a simple quotient. What we do is, suppose convert 5 Newton into dynes. Right? Let's consider this. And it can be done directly. We are aware 1 Newton is 10 to the 5 dynes. So 5 Newton will be 5 into 10 to the 5 dynes. 1 Newton is 10 to the 5 dynes. Therefore 5 Newton will be 5 into 10 to the 5 dynes. It can be done directly. But my intention over here is to make you understand the use of this particular formula. There are certain complicated quotients which we will encounter, which will make use of this formula to solve such quotients. Right? So let's do it. We'll proceed with the manner in which we have discussed just now. So, there are two systems. Newton is the SI and dyne it is the CGS. So, let's consider these two systems. One is SI, the other one is CGS. Here the numerical value is 5 and here the numerical value is to be determined. Right? Here M1 is in SI, it is 1 kg. L1 it is 1 meter, T1 it is 1 second. No doubt regarding this. In SI, mass, length, time are measured in kg, meter and second. This is CGS. Mass is in gram, length is in centimeter, time is in seconds. Right? And what is the physical quantity under consideration? It is force. And what are the dimensions of force? It is mLT minus 2. Right? M to the power A. So what is the value of A? It is 1. L to the power B. So what is the value of B? It is 1. T to the power C. So what is the value of C? It is minus 2. These are the dimensions of force in mass, length and time respectively. Clear? Now what was the formula? N2 is equal to N1. M1 by M2 to the power A. L1 by L2 to the power B and T1 by T2 to the power C. Let's substitute the value. N1 is 5. Keep on substituting the value. It is 1 kg. It is 1 gram. A, that is 1. L1 is 1 meter. L2 is 1 centimeter. To the power B, that is 1. It is 1 second. In CGS also time is measured in second. C to the power minus 2. Now look, 1 kg is 10 to the 3 gram. 1 meter is 100 centimeter. 1 second over 1 second will get 1. Okay. Gram get cancelled. 10 to the 3 to the power 1. We get 10 to the 3. Here we get centimeter will get cancelled. We get 10 to the 2. To the power 1 is 10 to the 2. 1 to the power anything would give us 1. So it is 5 into 10 to the power 5. That's the numerical value which we have obtained in CGS system. Right? You can do it directly as well. But students, note it down. I have discussed this formula because there are certain complicated cases where this formula is to be used. So you must know how to use this formula, right? I hope this concept is very much clear. And as I promised, we will certainly discuss some very good questions based on the three uses of dimensional analysis. Till then, just clear the theoretical concepts and I will be back with much more interesting numericals. Till then, goodbye.